Okay, I think we've got enough people here now, so welcome back, everyone. I thought we could talk about some of these problems involving the fundamental theorems of calculus today. Okay, before we just had a bit of an informal chat and we didn't record anything. But these questions are quite important and they show you the relationship between differentiation and integration, right? So who can tell me what is the relationship? What is the relationship between derivatives and integrals, or differentiation and integration? Who can tell me what is the relationship? What is the fundamental relationship? It's not a trick question. Who can tell me? Between the integration and differentiation, Vrudant, what is the relationship between them as processes? This is pretty much the basic idea from chapter 8 of the notes. So what is the basic, the fundamental relationship between derivatives and integrals? Who can tell me? Eddie, Ashley, Adam, Alan, Denzel, Vrudant, Wayun, Zach, what do you think? Come on, help me out here, people. It's been a long day.
Is it something like that if you have a function and then you integrate it and then you differentiate it, you get your original function back?
Yeah, it's similar to that. I think that's a good start, Vrudant. Essentially, in my mind, they're just opposites, right? So
Yeah,
a derivative undoes an integral, and an integral undoes a
undoes a
derivative.
derivative.
Yeah. So when we sort of differentiate an integral, we would expect things to sort of disappear in some sense, right? So let's have a look at a question today. So this is one that I've just done earlier. This is the basic first fundamental theorem of calculus. Okay, so the fundamental theorem of calculus number 1, fundamental theorem of calculus number 2. This says if you differentiate an integral, then these things cancel and you get this. This says that if you integrate a derivative, then it's just the primitive function evaluated at the two endpoints. Okay, so these are the most important things here. All right, so let's look at the question though. If I wanted to differentiate this, it's not quite in this form, right? See, a is a constant. So what I can do is flip it and change the sign, and then, hallelujah, I can do some differentiation. Okay, so the negative sign is going to come out the front, and then you can differentiate this. So cancel, cancel, and the x goes in. All right, and in this kind of format, what's the variable t? T is known as a dummy variable. Okay, so it doesn't matter what it is. T is known as a dummy variable. Okay, so you can have anything there, T, Y, Z, Q, elephant, not X though. Okay, you wouldn't really want X there. Okay, so that's pretty low on the difficulty scale. This is like an entry level problem for this particular set. But let's level up a bit, and we can look at the second fundamental theorem of calculus. So this was an application of the first fundamental theorem of calculus from here to here. But let's look at this second one and see what we can do. Okay, are there any questions for that particular example? It's pretty easy, right? As long as you know to switch this over, it's pretty easy. Okay. So let's go back to a slightly more involved question. Oh, it's a bit too big. All right, so I thought we could talk about 14a. This looks difficult, but actually it's not difficult at all in my opinion. Okay, so suppose you've got a function 1 divided by x. By considering the lower Riemann sums for f on this partition of this interval, show that log 2 equals this mess. Okay, so that looks quite difficult because, you know, oh, I've got a partition and I've got this crazy sort of sum and a limit. But actually, it's not too difficult if you draw a picture. Okay, so I'm going to show you what I did for that one, and we can discuss it together. Okay, so let me share with you what I've done, and I can just explain it to you. All right, so you start off with a function and you've got a specific interval. Okay, so here's the interval 1 to 2, and I've split it up according to the information that we're given. So, you know, they're all 1 on n units apart. That's the very left-hand endpoint. So this is x0, x1, x2, x3, blah, 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 xi, xn, right? So okay, so you slice it all up, you get your partition, and you look at the difference between the points in your partition. Okay, so it's 1 on n. Okay, so after you draw a picture, I've probably written too much there on the left-hand side, but after you draw a picture, it's very easy to actually compute this integral. Okay, so you can integrate it, you get that, and you just get log 2. So that's where the log 2 comes from in the final answer. Okay, so we'll draw on that a bit later. Okay, so let's set up a lower Riemann sum. Okay, so here's the graph of 1 on x. And this interval is like, you know, this arbitrary interval here. Okay. Now for lower Riemann sums, I want to look at the minimum value of that function on the interval. So it's a decreasing function, so I'll choose the xi star to be the right-hand endpoint of each interval. So that's where this comes from. Okay, so the width of your partition points, so the distance between one point and the next, is here. The value of the f is chosen to be the value at the right-hand endpoint of each of these subintervals. Okay, so that's 1 on n. This is going to be 1 divided by x plus 1. Okay. Okay, so 1 on xi star, which is just 1 on x sub I plus 1. Okay, so this is like, this bit is like your 1 on x I plus 1. Okay, so that's there it is essentially there. So I've just inverted that. The ends cancel, and what do you get? Well, if you write out the terms of this sum, that plus that plus that plus that plus that plus that, so you know that this and this have to be equal. Okay, so even though I've written a lot down in that question, and it's not an easy question. Okay, Sorry. Well, we haven't taken the limit yet. So when n goes to infinity, this and this will be equal. Okay. So the last thing that I want to do is to take the limits. Okay. So in there, I'll take the limits, and that is going to converge to the natural log of 2. Okay. So there's a lot to write down there. You don't have to write it all down, but you know, the important things to me, and it's not an easy question, is work out your partition, right? Or at least draw a picture. Okay. Do the simple integration and draw a picture. Set up your lower Riemann sum by choosing xi star to be the right-hand endpoint. Simplify this to get that, and you know in the limit this will have to equal that. Okay, so not an easy question, but the Riemann sums questions are not usually easy. Okay, they're a bit fiddly, and they're sometimes you have to really work hard at them to understand what's going on. But hopefully you're getting some idea of this particular solution. So let me know if you want me to discuss anything in great detail, because sometimes when you pre-prepare the solutions, you move too quick and people can't understand what's going on. So let me know what do you think of that kind of working, or that kind of question. What do you think? Let me know. Is there anything you want me to talk about in more detail for this one? Let me know. Okay, pretty cool way of writing natural log of 2. Okay, so there it is. Okay, let's do some other questions. Vruda, no, it's not the definition of log. In today's lecture, it's a good question. In today's lecture, I actually defined the logarithm function through an integral. Okay, so yeah, so with these things you can define them a few different but equivalent ways. But if you look at the recording from today's lecture, I actually defined the logarithm there using an integral. So it's pretty cool. Okay. Okay, so for part B is pretty much the same as part A. You've just got a different function and a different interval and a different partition. Okay, so if you just do what you did for part A and part B, it'll work out to be the same. All right, so let's look at integration by substitution. Okay, so basically the idea is to take a difficult integral and make it a simpler integral. Okay, that's the basic idea. So let's have a look at some of the questions and we can work through them. Okay. All right. So let's have a look at this first one. Integral of 1 on square root of x. Okay, there's a couple of ways you can do this. Can anyone suggest what an appropriate substitution would be for part A? What would you let u equal for this particular integral? Who can tell me? Who can tell me? If you were doing this problem, what choice would you make? There are several choices available, but what choice would you make to come up? I think, Vrudant, that's a good start. That's one of the choices. Let's have a look. Okay, so here I've used the Roudant substitution, u equals root x, and then made x the subject. And you want to compute the differentials and then substitute, right? So, when you substitute, you'll get a u there, you'll get a 2u du on the top. And yeah, I've just simplified that using a little bit of algebra. Okay, a little bit of algebra. And you want to get back to the x's, of course, the final answer in terms of the original variable x. So, that's one answer. Let's try a different substitution. Let's try u equal root 1 plus x. So you'll get a u down there. Okay. And so I've rearranged that to get that, and then taken the derivatives or the differentials again. And you'll get something similar to this, but not quite. Okay, something similar, but not quite, not exactly equal to that. Okay, so if I look at that, I'll get an integral like this, and I can divide that u in, and you get something like this. Okay, so up here I had an integral like this. Down here I've got a similar integral, but it's not exactly the same. Okay. So this is pretty easy to integrate. That'll become u, that'll become log of u. And yeah, you'll get an answer like that. Okay. So if you look, there's our first answer, there's our second answer. They're actually not the same. But can anyone tell me why it's okay to have an answer like that and a different answer like that? Does anybody know why that's okay? Let me know. They're both correct, Roudant, yes. Why is it okay to have different answers? Who can tell me? Why? Why is it okay to have different answers? Somebody should know this. Okay. Eddie, Ashley, Adam, Alan, Denzel, Roudant, Wayun, Zach. What's going on? Yeah, they only differ by a constant, right? You've got a 2 there, a k there, and a c there. So that's fine. That's fine. Okay. Last question, and then I'm going to hear from you. This is an integration by parts question. Okay, so this is 18 part A. I thought that was a good one to talk about. Okay, so integration by parts involves integrating products of functions. Okay, and it's a little bit harder to do, but you need to make a choice. Okay, here I've let u equal that and v dash equal that, and this is the integration by parts formula up here. And so you make two choices, you compute the derivatives, and from v dash you get v, and then you apply the integration by parts formula. Okay, and what you're hoping for is that this integral is simpler than this integral, and it is. It is. Okay, so integration by parts is a valuable tool when you are integrating products. Okay, and the way you want to work it is you want to have this new integral simpler than this original integral. If it becomes more complicated, it might be a problem. okay, it might be a problem. All right, so are there any questions for this particular example? Integration by parts is great, but if you make the wrong choice, sometimes it makes things more complicated. So the idea is make these choices so that this new integral over here is simpler than the original integral. Okay. And why have I written this? Well, remember this. Oh, this is just done by inspection, so that's another question. That's fine. Well, all right, folks. I'm going to stop recording now, and if there's any questions, feel free to speak up, let me know, or put something in the chat. So let me just kill the recording, and then we can have a bit of a chat.